Hi, I'm Amy. In this video, we'll take a look at a rational function and look at where it's undefined and figure out whether it has an asymptote or a hole there. Anytime you're investigating a rational function, like the one I have right here, you know that it will be undefined, which means it's discontinuous, for any x value that makes the denominator go to 0. If we look at the two factors in this denominator, I can see that if I plug a 2 in for x equals 2, this factor will go to 0, so the whole denominator goes to 0. And same thing for when x is equal to -3. This factor will go to 0. So I know that the graph of this function has discontinuities at both x equals 2 and x equals -3. But what kind of discontinuities? So I've written out the limit of our function as x approaches -3. What you'll notice is there's an x plus 3 in both the numerator and the denominator, which means that I can, as I'm looking at this limit, I can go ahead and sort of reduce that away and have an equivalent limit as x approaches -3 of 1 over x minus 2. Okay, I can't do that to the original function because that kind of takes away that knowledge of the discontinuity. But when you're looking at the limit, this limit is equivalent to this limit. All right, now let's try our direct substitution. When you plug in -3, we would get 1 over -3 minus 2, and that gives us 1 over -5, or -1/5. You might have noticed I didn't write the limit notation here. That's because I've already plugged in an x value, so I'm evaluating the limit. We really only need to include the limit notation when we're still investigating and trying to figure out what that limit is. So now that we know that our limit is -1/5, what kind of discontinuity is that? You'll notice that we had the x plus 3 and the x plus 3 cancel away. When you have a removable discontinuity, also known as a hole, that happens when the 0 part of the denominator does cancel away. So -3, -1/5 is the location of a hole on our graph. I'm going to go ahead and sketch that onto our graph, and then I'm going to investigate the limit as x approaches +2. So here I've got the limit as x approaches +2 of that same function we were looking at earlier. Remember, the first thing you always want to try is direct substitution. When I do that, you'll notice I get 5 in the numerator, and then I'm going to get a 0 times 5 in the denominator. That's not okay. I can't divide by 0. That tells me that this limit does not exist. In fact, if I tried to evaluate like 5 over basically something practically 0, that goes to either positive or negative infinity. What this does tell me, though, if I scroll back up here, it tells me that I have a vertical asymptote, because that's what happens when the 0 part of the denominator won't cancel away. You'll notice that x minus 2 does not have a counterpart in the numerator, so I can't cancel it away. But I do know I have a vertical asymptote at x equals 2. And I'll go ahead and sketch that on the graph now. So in fleshing out the rest of the graph, it can be useful to look at a few more limits. For instance, what happens on either side of that vertical asymptote? So let's take a look at the limit as x approaches 2 from each side of that asymptote. So this represents the limit as x approaches 2 from the left. That's why there's a little minus sign. This represents the limit as x approaches 2 from the right. That's why there's a little plus sign. You'll notice I'm using the simplified version of the limit. I went ahead and reduced the x plus 3's just to keep things simpler. Now, if you plug in exactly 2, you're going to get 1 over 0, which is undefined. That means our limit does not exist. But we want to figure out, where is it heading? So in each case, I'm going to use an arrow because I know my limit does not exist. But in each case, the numerator is still 1. The denominator is getting closer and closer to 0. Here, since we're coming in from 2 from just above, a value like 2.0000001, our x minus 2 is going to be practically 0, but also slightly positive. So I'm going to write plus 0 here. I know that's strange notation, but that tells me it's practically 0, but slightly positive. And positive over positive tells me that this is going to be a positive output value, and 1 divided by 0 tells me it's going to infinity. So even though that limit does not exist, it is heading towards positive infinity. And then on the other hand, here we're plugging in a value just below 2, which means that even though it's going towards 0, our x minus 2 is going to be slightly in the negative side, which tells me that the output values are heading towards negative infinity. Of course, that also means that the limit does not exist, but at least we know what direction the graph is heading. So let's go ahead and enter that on the graph so we can get a more clear visual. So again, from the left, we were having our graph head towards negative infinity, and from the right, the graph will be heading towards positive infinity. Now let's take a look at the end behavior and see what happens as x gets really, really big and gets really, really small. Those are the limits as x approaches positive and negative infinity. Here are my limits as x goes to positive and to negative infinity. Now, in both cases, we have 1 on top and we'll be dividing by something infinite. So I know in both cases, that limit is going to go to 0. However, in the case where x is going to positive infinity, this fraction will be a positive over a positive, telling me that we're approaching positive 0, meaning we're coming in towards 0 from above. And in the case where x is approaching negative infinity, this fraction will be positive over negative, telling me I'm coming in towards 0 on the graph, but from below. So graphically, that's going to look like this. As x goes towards positive infinity, our function goes towards 0 from above. As x goes towards negative infinity, our function goes towards 0 from below. And of course, that means we have a horizontal asymptote at y equals 0, because you find horizontal asymptotes with limits as x goes to positive and negative infinity.